From Tokamak network. Today I'm gonna introduce the monitoring data in Optimistic Rollup. It's called the Randomized Attention Test. Shortly, you can call it RAT. And I'm really excited to give a talk in Ethereum Community Conference. And thanks for taking your time for attending. So I guess you're familiar with the rollups. So, but in optimistic rollups, the correctness L2 is assumed by default, and it proven indirectly by further proof. And it has dispute window, usually 7 days, and during 7 days, it guarantees that validators can challenge the potentially incorrect the state by proposers. So the problem is if the block proposers are submitting correct statement constantly, then it means that you don't see any the on-chain validator activities. So, in the real world, there were only few the fruit-proof cases. So it means in years of the optimistic rollups, validators are very silent on-chain. So there's a concept called verifier's dilemma. This concept was originally proposed by the Loy Lu in 2018, 15. Okay, so shortly it means if all the others, you are a verifier, but all the others verify, then you are economically not motivated to verify because all the others verify the state, then you don't need to, right? So, however, is it a real-world risk? I think it's controversial, but I think if validators are really silent, I don't think we can fully trust the validators. And also, I think, for example, in big rollups, when big DeFi apps, they deploy their apps in one specific rollup, they try to operate their own validator to mitigate the risk. So it means still there's no big trust on validators, and you don't see even validators are online or offline. So the attention test is to propose to solve this problem. So let's pass this slide. So attention test is a mechanism to verify validators are actually monitoring the chain, so to test their online and offline, or they're following the state change or not. So this idea has been proposed and discussed for years ago, but the thing is that nobody tries to design or implement this concept. So why? Let's guess. Actually, we don't know the real reason, but maybe I guess. There's a still belief that current security models are enough for optimistic rollups because currently, as far as I know, there's no big hack about the optimistic rollup security. And maybe there's an assumption that validators are trustful, or the one reality is that optimistic rollups are currently still very centralized. So maybe it means you can trust them. But if we don't use these assumptions, then we need something like another mechanism like attention test. So here's the core concept of the RAT. So in attention test is randomly triggered. It should be randomly triggered with posting the L2 state. And second, the target validator is randomly chosen. And the attention test is a puzzle that's submitting the closest Merkle leaves to construct a state root. So, for example, the proposer doesn't need to change their parameter. They constantly submit the L2 state, but it can be just posting the L2 state or it can be attention test. If attention test is triggered, then validator should submit closest Merkle leaves that can construct the L2 state. So it's very compatible with current optimistic rollup designs. But here's a problem. In the previous talk, somebody asked about the randomness. Yes, on-chain randomness can be expensive, complicated. But in this mechanism, we use weak randomness by on-chain. And I will address this problem in the later slide, and we will say this weak randomness, something like using a block cache will be enough. And I should say point out one limitation that this puzzle guarantees that they are following L2 state, but it doesn't guarantee that it will process the dispute, the pipeline. Because of we can refer the Chroma case. There was one real-world dispute challenge in Chroma, the one opt-in rollup. Unfortunately, it recently closed their mainnet, but their validators found the wrongly constructed the L2 state, but they found at the same time that they found the smart contract can't process their dispute, the challenge. So they had to upgrade the smart contract to solve that problem. So here's the randomized attention test flowchart. So here are the existing rollup procedure: state transition, post commitment by proposer, and waiting for fraud proof. If there's a fraud proof, dispute game, and then after 7 days, finalization. So if RAT can be integrated simply with PA probability, the proposer will post the attention test. That is same the L2, the Merkle root, but in this, if smart contract decide it's not just commitment, it's just test, then designated validator should submit the closest, the Merkle leaves that can construct the Merkle root. So if validator is live, then the validator will submit the on-chain, the solution to the smart contract. Then if it's not live, then it will fail, then timeout. And even if it passes the solving the attention test, then still it goes to fraud proof, because the proposer and this designated validator share the same, the state change view doesn't mean that this state change is correct. So it still goes to the dispute window, and if state mismatch or the validators, the submission solution doesn't match to the L2 state, then it will go to the dispute game and try to solve it. And here's the flow in the view of the smart contract. So proposer submits attention test puzzle with the L2 block number and the state root, and then the RAT contract this determines it will be the attention test or not. And if test is initiated, it emits event, and if target validator is live, then it will submit the solution, and the smart contract will verify very simply by just the hash, the computation. So we can absolutely deploy the RAT mechanism, but the problem is the frequency of these tests, the PA, and what will be the penalty. So we analyze using the game theory framework. The full analysis is in the paper in the last slide, but let's go simple. So there are multiple necessary equilibrium, but the equilibrium we want is the strategic equilibrium we want to force for the validator and proposer will be this, right? The proposer action is always honest. It posts always honest state transition, and the validator is always online. So we want this equilibrium, and then the result of analysis says, okay, and the result of analysis says that this graph. So for example, if we just, for example, there are like 10 validators, and if we put the attention test penalty, failure penalty as like a $500, then we only need the 0.028% per epoch. It means we need only 0 and 4 tests per day of attention test is enough to force this ideal equilibrium. And so it means just 1% of attention test trigger will force the ideal security equilibrium. Then the question is, we use the weak randomness, right? That it means the powerful or smart or rational proposer, malicious proposer, will try not to trigger attention test when try to state fraud state, right? Then it's a rational strategy. But in this payoff table, in the fraud state posting case, the attention test, the penalty doesn't affect the equilibrium condition. So that's why I'm saying that we can use just weak on-chain randomness, and it means we can construct this mechanism simply. So what is the expected cost to construct this mechanism in smart contract? So here are guess estimates. So state transition, existing state commitment costs about 90K gas. And if we post attention test, then it gives 160K gas. So, but it's mostly caused by attention test information storage. And attention test solution transaction costs like 27K, but we don't post the attention test trigger every time. It's just less than 1% is enough, as I mentioned. So this cost overhead is very manageable, I can say. Then what's next? About this rat mechanism, I think our game theoretical analysis should be purely reviewed in a like academic level, and there should be implementation and network level testing that can be released, and then why we need such an additional mechanism for optimism rollup, because current dispute window is too long, like 7 days, and as far as I know, at my best knowledge, 7 days doesn't have any theoretical basis. It's just consensus. But and also, so we need shorter dispute window for our user experience, and so we need, I can say we need the dynamic dispute window and shorter dispute window. But the problem is engineering and calculating the dispute window is very challenging, but I think we can engineer comparatively. So let's say we can say 7 days enough with any additional mechanism. Then if we add such mechanisms, then we can make it shorter than based on the 7 days consensus. And also another direction for the optimistic rollups will be definitely hybriding GK Freud proof, because the bisection game of the Freud proof mechanisms are very, very complicated. So that's what I want to say. And this is the end of the talk. And thanks for taking your time. And any questions? And also, here's a paper of this mechanism. Thank you.
Here you go.
So, thanks for the presentation. So quick question, how do you prevent Sybils from verifying attention tests? Because here I see you reconstruct the Merkle proof, but they couldn't just fetch the storage from RPC or from another node. And how do you fix that?
I don't fully understand your question. Can you?
So if I understand it correctly, the attention test is fetching, providing a leaf from the state, following a Merkle proof of state of the leaf. But what prevents them from using an RPC to retrieve that proof and use another node? And hence you could have Sybils just pretending to be nodes and passing the attention test here.
Yeah, that can be an issue. Good point. But that means the validators can still query such the states from other validators. It means then still they can follow the states, I think. Then validator should depends on such RPC. Then that's the validator's own risk. I think.
Basically, you can have full validators pass your challenge using RPCs, alter RPCs that are public, that are open, and just fetch your proofs directly without having producing any computation themselves.
Can you discuss it in coffee break? Yeah, thank you.
Any more questions? Thank you so much, Suhyeon Lee.
Thank you.